Hi everyone. So this is Satish. Happy to meet you again. So this time I am going to talk about some important aspects in colloids. Okay. So the basic thing in colloids. Okay. So what are called what is dispersed phase and the dispersed medium. Uh, what are their impact? What are the differences between lyophilic and lyophobic colloids? Okay, so all those things. So even the electrical properties, optical properties, uh, so all those things. So, but many of you are not familiar in this topic, namely origin of electrical double layer in colloids. So most of you uh, forget about the colloids are charged in nature. Colloids are charged in nature. Okay, so they have some charges. So they're not a neutral molecule. They have some charges. So only because of those charges, they couldn't settle at the bottom. They couldn't settle at the bottom. So as far as the colloids are concerned, they are always in a random motion. They are always in random motion. So absence of the charges in colloids will make them to settle. Okay. So what is behind this mechanism, or what makes the colloids to undergo random motion? So that is explained by your electrical double layer. Okay, so let us go into the points. So it's a theory. So electrical double layer theory describes the formation of charged region at the interface between the colloidal particle surface and the surrounding electrolyte space. So what is meant by charged colloidal particle surface? So if you consider one particle, namely ferric hydroxide, ferric hydroxide. So many of you have learned it from the book that ferric hydroxide particles are positively charged because the Fe3 plus settle around the ferric hydroxide and it makes the ferric hydroxide particle as a positive one. Okay, so let me explain all these things in the next slide. So what's the importance of this phenomenon? So this phenomenon is crucial for explaining the stability of colloidal systems. Okay. So as far as the electrical double layer operates in colloids, they won't settle at the bottom. They won't settle at the bottom. So otherwise they will undergo vioculation. Okay. So it is only the electrical double layer that prevents the colloidal systems from undergoing vioculation. See, so in this slide, you can view the things. So this is the rough sketch of electrical double layer. Electrical double layer. So this is your charged colloidal particle. Charged colloidal particle. Okay, so this is your charged colloidal particle. So in this diagram, I have given the negative charge. So the negatively charged colloidal particle is surrounded by full of positive charged ions. Positive charged ions are present around the negative charged colloidal particles. Okay, so these positive charged ions bind tightly with the surface of the negatively charged colloids. So this is negatively charged colloid. So on the surface of the negatively charged colloid, the positive charged ions got absorbed on its surface. Okay, so it forms a strong and rigid layer or it is called stationary layer. It is called stationary layer. So this stationary layer is surrounded by one more layer that is from liquid. One more layer that is from liquid. So it is called diffused layer. So in the diffused layer, ions are diffused more freely around the particle. Okay, so they move freely around the particle, so there is no restriction as far as diffuse layer is concerned. But in the case of your rigid layer or stand layer, the particle will attract the ions of opposite charge. That is, the counter ions are attracted. Counter ions are attracted. So the positive ion will move closer to the surface. So this positive ion move very closer to colloidal surface. So this is the colloidal surface. Okay, so this is colloidal surface. So this colloidal surface, so in this colloidal surface, the positive charged ions bind firmly with the negatively charged colloidal surface. So these ions are tightly bound immediately around the surface. Okay. So up to this you can understand, I think. Okay. So there are two layers. One is the rigid layer or stern layer, and another one is diffused layer. So in the diffused layer, ions move freely around the particle. Okay. So let us move to the next slide. Okay, so in the fixed layer, so according to Helmholtz, so actually this electrical double layer is explained by Helmholtz. So according to Helmholtz, there are two layers. One part of the layer is known as fixed layer. So what is the other name for fixed layer? It is stern layer. So the stern layer has both positive or negative charged ions adsorbed to the colloidal surface. Okay, so either positive charged ion or negative charged ions are adsorbed to the colloidal surface. So in this diagram, I have mentioned only the positive charged ions bound to the negatively charged colloidal product. Okay. So another part of the layer is that it is called a diffused layer. So it extends to liquid phase. Okay, it extends to liquid phase. So in the diffuse layer, you can find both positive charged ion and negatively charged ions. Okay. So what is the importance of fixed layer? So other thing is stationary layer. So it occurs next to the surface of the colloidal particle. Surface of the colloidal particle. Okay, so this is your fixed layer. This is your fixed layer. So this is your fixed layer. Yes. So this is your fixed layer. So this is the colloidal particle surface that is mentioned here. Next to the surface of the colloidal particle. So in this layer, the positive charged ions are bound to the surface firmly. Suppose if the positively charged ions are present at the center of the colloidal particle, then the negatively charged ions will surround the surface of the colloids. Okay. So it arises due to adsorption. So how does it happen? All happens by means of adsorption. Okay. So next one is your diffused layer. So diffused layer is another layer. It occurs next to the stern layer. So what is the other name for diffused layer? Bulk liquid layer. So in the diffused layer, both the negative and the positively charged ions are in random modes. Both the positive and the negatively charged ions are in random motion. Okay. So all these things are collectively explained in this slide. Fixed layer attracts the oppositely charged ions in the medium. This leads to the interface that separates the electrical double layer. Okay. So let me explain this electrical double layer theory by means of one example. So you just imagine the simple reaction between sodium iodide and silver nitrate. Sodium iodide and silver nitrate. So you dissolve the sodium nitrate in water and you keep it in one test tube, and you have silver nitrate salt in another test tube and have some water just to shake it for a while. So here the condition is the larger amount of sodium ions and iodide ions are present. So in this ionic solution, larger amount of sodium ion and iodide ions are present. And they are mixed with this silver nitrate solution, which contains minimum number of feeble number of Ag plus and NO3 minus ion. What happens? As expected, silver iodide precipitate is generated. Silver iodide precipitate is generated. But one thing you have to keep it in mind, since I minus and Na plus ions are present in larger numbers, here I minus ion form a fixed layer. I minus ion form a fixed layer. So what is the counter ion of the I minus ion? Is sodium ion. Sodium ions are present in the colloidal solution. So the interaction between these two ions, the interaction between these two ions will generate a potential. This potential is called zeta potential. So it is called zeta potential. Okay. So this potential is called zeta potential. So this potential is equivalent to that of the potential produced by capacitor. It's produced by capacitor. So what is the importance of this zeta potential? Higher the zeta potential, strong repulsion occurs in the colloidal system. Strong repulsion occurs in the colloidal system. Suppose if there is no repulsion in the colloidal system, then all the particles will come to grinding halt and coagulation occurs. Okay. So the generation of the zeta potential is very, very important. So where does the zeta potential generate? So at the interface of diffused layer and the Stern layer. At the interface of diffused layer and Stern layer. So this is once again explained in this slide. The precipitated silver iodide particles selectively absorb I minus ion from the solution. Selectively absorb I minus ion from the solution onto its surface. Okay. So this forms a negatively charged fixed layer on the particle surface. Okay. So at the same time, the positively charged sodium ion from the solution are attracted to this negatively charged surface, forming a mobile or diffuse layer around the fixed layer. So can you understand? The precipitated Ag particles selectively absorb I minus ion from the solution on their surface. On their surface. Okay, let me draw it. Or I can draw it here. You just imagine the silver iodide solution in the silver iodide precipitate. So some positive charge is generated now. So this positively charged ion is surrounded by negatively charged particles, Ag minus. Okay, Ag minus, Ag minus, Ag minus, Ag minus, again Ag minus, sorry, I minus. So this I minus ion binds strongly with the surface of the colloidal particle. surface of the colloidal particle. Okay. Since Na plus ions are present in large numbers, so the silver iodide precipitate is surrounded by this I minus ion since they are present in large numbers. Since they are present in large numbers, the I minus ion forms a stationary layer. So the stationary layer is surrounded by diffused layer. So in the next step, so in the diffused layer, you can have both the type of ions. Na plus ion, Na plus ions are there. And the one more negatively charged ion, it is MO3 ion also. So all those ions are moving in the diffuse layer. Okay. So at the interface of the diffused layer and the stand layer, some potential is developed. So this potential is called zeta potential. Is called zeta potential. So zeta potential is very important as far as stability of the colloids are concerned. When the zeta potential is higher, the zeta potential is higher. When the zeta potential is higher, the colloids are stable. When the colloids are stable, they won't settle at the bottom. More stable the dispersion. Okay, so what is the application of this electrical double layer theory or the zeta potential? So this topic is very important for the industries for optimizing the formulations, controlling the particle interactions, and also to ensure the quality of their products, in pharmaceutical industries, water treatment, even in the paint industry, because all of you know that paint is also a very good example for colloidal dispersion. Okay, so nowadays more and more companies are coming, more competitors are coming. So therefore, they have to keep their paints intact for a long duration. Okay, so for that, the zeta potential is very, very important. When the zeta potential of their paint is very low, their quality is not up to the standard. Okay, so it is understood that their quality is not up to the standard. So therefore, they have to enhance certain parameters to improve their quality. Okay, so I think you are familiar with this topic. So the electrical double layer, it has two layers. One is stand layer and another one is diffuse layer. So at the junction of the stand layer and the diffuse layer, it leads to the generation of zeta potential. So this zeta potential is equivalent to that of the potential generated by the capacitor. Okay. So another important thing. So yesterday while I am preparing the slide for this, I come across this question from CSR examination. Okay, so actually this question is asked in CSR June 25. In June 25, this question is asked. CSR June 25, this question is asked. So what is the question? In a colloidal solution, zeta potential is the electric potential at the dash. So what is the answer for this? Radius of colloidal particle, or the radius of stand layer, or the radius of shear surface, or the outer radius of diffuse layer, or the outer radius of diffuse layer. So what is the answer now? The radius of shear surface. Radius of shear surface. So it is asked in 2 mark question. Asked in full mark question. So it's very easy. Okay. So I think this video will be very useful for the students who are preparing who are studying colloids. So at the same time, you could see some competitive, you could find some questions which will be very useful for competitive exam also. So thanks. Thank you, students, for your patient listening, and I will meet you soon with some more lectures. So thank you, one and all.